Electron configuration is one of those topics that can feel overwhelming at first, with orbitals, subshells, and all those numbers and arrows. But once you get the hang of it, you'll see how it unlocks a deeper understanding of the periodic table, bonding, ion formation, and more. In this video, I'll break down what electron configuration actually means, how electrons fill shells and orbitals, and how all of this links with the layout of the periodic table. No need for rote learning again. So by the end, you'll not only know how to write electron configurations with confidence, you'll understand why they matter. Let's get started. Let's start with what we know from GCSE. So at GCSE, you may have come across the idea that electrons are arranged in shells, and in the first shell, closest to the nucleus, then 2 electrons fit in there. In the second shell, 8. The third shell, 8. And then the fourth shell, 2. And that's because at GCSE we only teach up to element 20, which is calcium, 20 electrons. Now, those shells we say represent the distance from the nucleus. So the first shell is closest, the fourth shell is furthest away. Some teachers, when they get to A-level, go, that's all a lie. It's all a lie and none of it is correct. Actually, what it is a massive oversimplification. And here I've mapped on the A-level configuration to that GCSE model, so you can see a little bit more about where that simplified version came from. It doesn't mean it's completely false. It just means it's only telling a very tiny part of the story in terms of electrons. So you may have come across the electron configuration written now at A-level as 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d10. It does go on from that. Now I've mapped this using the arrows to the GCSE configuration. So in the first shell, the big number 1, meaning the first shell, the superscript says 2, so 1s2. That means there are 2 electrons in the first shell. Then if you look at every part of that electron configuration that has a big 2 in front of it, that's the second shell. Those superscript numbers, the 2 and the 6, add up to 8. So 8 electrons in that second shell. And so on and so forth. So the big number 3, the third shell, then we have 8 electrons there. And then the point at which we stop at GCSE and that fourth shell, 4s2, 2 electrons there. So there you can see how they map together. Let's now break this down a little bit more so you can see what does that actually mean. Like at A-level, I just wrote learner. I didn't have a clue, to be honest, about what the different aspects mean. So let's drill down into that understanding next. So the bits in orange here, the words in orange, that's what I really want us to focus on here. This is the key understanding at the heart of electron configuration. We have 3 pieces of information presented to us in our A-level electron configuration. We have the big numbers, 1, 2, 3, 4. Now they still represent the shells or energy levels. And those words are equivalent depending on which syllabus you are studying, so you could use those words interchangeably. Now the shell or energy level that the electrons are in represent the distance from the nucleus. So the first shell is still the closest, followed by the second, third, fourth, and so on and so forth. So the big number is distance from the nucleus. The second part of the electron configuration, that is S, P, D, etc., that are F as well, that represents the subshell or sub-level. Now, this bit is very easily misunderstood by many. Now, the S, P, and D refer to the energy of the electrons. And D electrons have higher energy than P, and P electrons have higher energy than S. So if we look at part of that electron configuration now, 2s2, 2p6, let's see what this actually means. So the big 2 means that it is all of those electrons, all 8 of them, 2 and 6, are in the second shell. The S and P means we have different energy
of electrons in those shell. We have some at a lower energy, 2 electrons at the lower energy s electrons, and 6 electrons in the p subshell that have higher energy. Those electrons are the same distance from the nucleus because they are in the second shell, but they are at different energies. So subshells or sublevels are all to do with the energy of the electrons. It does not mean that they are further away or closer. It does not tell you about distance. That's the shell number. And then finally, we have the superscript numbers. Now those superscript numbers represent something called orbitals. And those orbitals are regions of space where 2 electrons are most likely to be found. So they are different shapes and sizes. They are theoretically modelled so that we have a shape and size for them. But within that shape, we will likely find 2 electrons. Now, if you have an s subshell, then we have 1 orbital, 2 electrons in there. If you have a p subshell, that is broken up into 3 orbitals. Each of those fits 2 electrons in, so that is 6 electrons in total. The d subshell, that has 10 electrons in. That's split into 5 orbitals, each one of those with 2 electrons in, if that is full. So key takeaways from this. Watch this again as needed. The big number is the distance from the nucleus, how far away the electrons are. The SPD is the subshell or sublevel. That tells you about the energy that the electrons have. And then orbital tells you where those electrons are most likely to be found. Okay, now let's look at how you can actually remember this. So my A-level teacher way back when just presented this to me and I went 1s2, 2s2, 2p6, 3s2, 3p6, and I just chanted it off. Whereas actually I'm saying you don't need to do that. I come from the place of understanding this is always better. And if we can minimize the amount of rote learning you have to do, then that is amazing. So what we can do now is map this to the periodic table. Meaning, if you have a periodic table, you can literally read electron structures off them without having to remember that chant the way that I did. Now, in order to be able to do that, we need to understand that the periodic table is actually split or arranged into S, P, and D blocks. And I've given you the definitions there. We meet them again at other topics at A-level. So when I say the S block, what I mean is those are a group of elements, all with their highest energy electrons in an S orbital. When I'm saying P block, I'm describing a whole group of elements with the highest energy electrons in a P orbital. And I think we know where this is going. The D block is a group of elements where the highest energy electrons are in a D orbital. Let me show you what that looks like. So here, I've color-coded the periodic table so you can see it split into the S, P, and D block. Now, the S block is what I've colored orange or yellow on the periodic table. Now, those elements in the S block, they all have their highest electrons in an S orbital. The P block you can see in green, and the D block you can see in purple there. And again, you might be thinking, oh, how am I reading this off? Okay, let's break it down further. So we can see where the highest energy electrons are. Now let's map it to how to read the electron configurations. So let's start off with hydrogen. So if we look at the period, which is the rows across the periodic table, then hydrogen and helium in the first period. That means their electrons are in the first shell closest to the nucleus. That is an S orbital because they are in the S block. And then hydrogen has 1 electron, 1s1. Helium has 2 electrons, 1s2. Then we move on to the third element, 3 electrons. So lithium in the top left-hand corner, 3 electrons, 2 of them are in that first shell, 1s2. One of them is in the second shell in an s sublevel, so 2s1. So the whole configuration for lithium looks like 1s2, 2s1. Element number 4. If I look at beryllium, we go read across 1s1, 1s2, 2s1, 2s2. Piece that together. We therefore have 2 electrons in the first shell, 1s2. 2 electrons in the second shell, both of those in s sublevels, 2s2. Next one. Element number 5, which is boron. We read across, starting right at the top with the hydrogen, 1s2. Then go to the next row, 2s2. Keep reading across, we hit boron next, 2p1. So that is 1s2, 2s2, 2p1. Now let's skip through to oxygen. So oxygen, you can just see it peeking where the number 16 is there. We're going to read all the way across. So we're going to start with that first row, 1s2. Then we skip to the second row, the second period, 2s2. And then oxygen, we count across the P block, 1, 2, 3, 4, 2p4. Okay, let's skip along a little bit further and look at something now in the D block. So let's pick, I'm just referring to my periodic table here, titanium. So titanium, you can see, is a little 48, just peeking out there in the purple D block. Let's read across. So starting with 1s2, the first period. Then we skip to the second period, 2s2, 2p6, keep reading. Next period, third period, 3s2, 3p6, 4s2, and then if we're doing titanium, count across 1, 2, 3d2. Now, I appreciate that might have been quite quick. We're going to practice this more and more, so do not panic at this stage. We'll come back to this in a second. And if you're enjoying this so far, don't forget to click subscribe right now. Okay. So here are a couple of principles that are really important when it comes to arranging electrons. Now, one of them is called the Aufbau principle. You probably don't need to worry about remembering the name of the principle, but we do need to understand what it tells us. Now, the Aufbau principle says that electrons enter the lowest energy orbital available, i.e., if you are hydrogen with 1 electron, that's not going to go into the 4th shell or the 5th shell. It's going to start off with the lowest energy orbital available, which is in the first shell. It's that 1s. It's like, for example, if you are on a bus and, I don't know, you're entering that bus feeling pretty tired. It's easier to sit downstairs than it is to climb upstairs. So electrons like to not climb upstairs. They're going to go into the lowest energy available and then fill up from there. Now, Hund's rule tells us that electrons prefer to occupy orbitals on their own, and they only pair up when there's no empty orbitals of the same energy available. What do I mean by that? Let's go back to that bus analogy. So you've got onto the bus and you look down the bus on that lower floor. There's lots of people there and their seats are usually in pairs, aren't they? And correct me if I'm wrong, but usually everyone sits separately to begin with. So they always go on an empty seat. And only then, when there's no kind of empty pairs left, do people start sitting next to each other, presuming we've got a bus full of strangers here. Okay. Now what this does is electrons are negative and they repel each other. Okay, always. But if they fill separately first and only then pair up, overall it's reducing electron-electron repulsion, and that's more stable. So we always, when we are doing our electron configurations, fill the lowest energy orbitals first. And where there is not many electrons in that subshell, we always place one electron separately in each orbital. When we run out, then we start to pair them up. And here we can see that visually. So if we're looking at silicon, silicon is element number 14. That means it has 14 protons and as an atom, 14 electrons. Now those electrons are going to start with the lowest energy filling there first. So those are the 1s2 you can see in the bottom left-hand corner. Then it has enough electrons to fill the second shell. So that's our 2s2, 2p6. There's still 4 electrons to go. So then it starts to fill 3s. And then when it comes to 3p, there's only 2 electrons in that 3p sublevel. So we separate those out. We don't pair them up. They separate to begin with. So that overall gives you the electron configuration of 1s2, 2s2, 2p6, 3s2, 3p2. And you can see there how they are arranged in the orbitals. Now, there's an important thing to notice there too. So there you can see that 4s is lower in energy than 3d. And that should also say that 4s is lower than energy than 3d when these orbitals are empty. And that means we fill 4s electrons, 4s orbitals first, and then 3d. And you can see that when it comes to calcium. So calcium is element number 20. And that means it has 20 protons, 20 electrons. We start to fill from the lowest energy orbitals available, so starting with the 1s. Once you get 3p full, and when we filled that 3p, remember we filled it 1, 2, 3, then we pair them up, 4, 5, 6. Rather than filling 3d next, 4s is the one that is lowest available energy next. So the 2 electrons fill 4s. If it had any more electrons, and we were talking about different elements here, it would fill 4s and then 3d. Okay. Now let's look at ions. Now the rule to follow for ions is that the highest energy electrons are lost first when an ion is formed. So we fill from the lowest energy electrons, and then we empty from the highest energy electrons. And because chemistry is fun like this, there's always an exception. 4s electrons are now removed before 3d. So what do we mean by that? When we are filling our orbitals, remember 4s was lower in energy, we fill it first. Once 4s is full of electrons, it jumps up in energy. And once it's full, it is higher in energy than 3d. So we take those away first. So you can see, for example, calcium there as an ion. It was 3p6 4s2. The highest energy electrons there are the 4s ones. If it is calcium 2+, it has lost 2 negative electrons, and both of those are lost from 4s. And we're not done with the exceptions. There are 2 other sections to be aware of, and those are copper and chromium. Now, they don't have that expected electron structure, and therefore they're the only exceptions that you can't just read off the periodic table. So chromium, for example, if we were reading across, would be 4s2 3d4. However, it's not. Rather than being 4s2 3d4, it becomes 4s1 3d5. So it half fills both of those. Now, there's nothing special about a half-filled orbital. They're not inherently more stable. However, that overall electron configuration reduces electron-electron repulsion and overall is more stable. And that's why it has that structure. Copper, on the other hand, if we just read off the periodic table, it would end with 4s2 3d9. And that is not what it has. It actually goes to 4s1 3d10. Again, overall, that's just a more stable electron configuration. If we have those as ions, the same rule applies. We still remove the highest electrons first, the highest energy electrons first, which means you're still removing 4s before 3d. It's time to practice. So here we have some atoms and ions that we're going to try and write the electron configurations for. Now, if you're feeling confident, this is the perfect place to pause this video, have a go, and then hit play again when you're ready to check your answers. It would be really helpful to have a periodic table to hand so that you can read things across as you go. And when you're ready, let's look at the answers. I'll be explaining these as we go through them too. So let's start off with the atoms on the left-hand side. So reading across the periodic table, carbon is element number 6. So 1s2, 2s2, 2p2. Then phosphorus. So phosphorus is in the P block. Read across through your periodic table and ending there in 3p3. Calcium we already met, ending in the 4s2. And vanadium is one of those D block elements. So we fill 4s first and then count across that D block. Vanadium is 1, 2, 3, 3d3. When it comes to the ions, so let's look at nitrogen first. So nitrogen is element number 7. So as an atom, it should have 7 electrons, and that would fit into 1s2, 2s2, and then 2p3. Now, when it's an ion, N3-, it's gaining 3 negative electrons. So it goes from 2p3 to 2p6. Okay, potassium. Now, potassium as an element is element number 19 electrons. So if we were to read across the periodic table to find out its electron configuration as an atom, it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Now it loses its highest energy electrons first, and it has 4s electrons, so there are what are going to go first. Potassium as a 1+ ion has lost 1 negative electron, so bye-bye 4s1, that's gone. Then let's look at vanadium. So vanadium, we already did the electron structure as the atom on that left-hand side. So we know it's ending in 4s2, 3d3. For it to become a vanadium 3+ ion, it needs to have lost 3 negative electrons. In order to lose those 3 negative electrons, highest electrons first, so the 4s are lost first. And then the third electron is lost from D. So 4s2 is gone, and then the third electron comes out of that D, so it goes from 3d3 through to 3d2. And then finally, chromium. Now, hopefully you spotted that chromium is one of our exceptions. So it doesn't have that typical expected structure that you could read off the periodic table. Let's map that out as an atom and then look at how we come to an ion. So we have 1s2, 2s2, 2p6, 3s2, 3p6, and then we have 4s1, 3d5 as an atom. When it becomes an ion, it loses 2 negative electrons. The 4s1, that's the highest energy electron, so that is lost first, and then it loses its second one from D. So 4s is gone, and then it becomes 3d4. And there we go.
Once again, thanks for watching, and if you found this useful, then don't forget to like and subscribe now. And if you want to learn more about A-level chemistry, this topic of atomic structure, then check out my next video.